So in this video, I just wanted to go over a few examples from the chapter 23. And we're looking at flux and how the change in flux over time of a magnetic field can help generate a voltage, an EMF, right? And so the next few examples are going to talk about that. This first example has to do purely with flux, though. And so recall the definition of flux, okay, is the magnitude of the field over the area that it's penetrating multiplied by the cosine of the angle between the two. Now, one note, okay, a word to note. Remember that the normal, okay, this normal here is the direction that's associated with the area, okay? So if that area is perpendicular to, if the plane itself, I guess I should say, is perpendicular to the field, then that means the normal to the area is parallel with the field. All right, so that's why this is a cosine instead of a sine. Okay, that's why this is a cosine instead of a sine. If the angle between the normal and the field is 0, then that means that the field is going straight down through into the area. Okay, so in this first example, suppose we have a sheet of length 0.2 meters and a width of 0.3 meters, and it's embedded in a magnetic field of strength 0.5 Tesla, and we've got our figure here. We want to find the flux if the angle between the sheet and the field, and by the way, the angle between the sheet means the normal that's associated with the sheet, okay? The angle between the normal of the sheet and the field is 50 degrees. And then part B, what is the maximum flux through the sheet? So if I reorient either the field or the sheet so that the flux is maximized, then what will that flux be? Okay, so in the first case, we literally just take our values and we can plug into the definition of flux. Got my 0.5 Tesla field, 0.2 meter length, and 0.3 meter width. And so the area of a sheet is my length times my width, right? So this is the field B. Here's my area A. And the cosine of the angle between them, right? And when you run that calculation, you get 0.019 Teslas times meters squared. So that is the unit of flux, right? Because we're looking at the total amount of magnetic field that is penetrating an area. So it's field times area, or Teslas times square meters. Now the maximum flux is going to be when the sheet and the field are oriented just right? And that occurs if I have a flat sheet, right? And the flux is going to be penetrating that sheet, and the normal to the sheet is straight down, and so in that case the normal and the field are parallel to each other, and so in that case the angle between B and the normal is going to be 0, right? So the angle in that situation is going to be 0, and so the maximum is going to occur at the 0 angle situation as the cosine of 0 goes to 1. And in that case, I just have to plug my area multiplied by the field into my calculator, and I get a maximum flux of 0.03. Okay, so there's the maximum flux. Problem 23.7, okay, asks us to find the units on this quantity, change in flux over change in time, and show that it actually does indeed give us the units of volts. Now it needs to give us the units of volts, right, because of the relationship E is equal to delta phi over delta t, right? So if E is an EMF or a potential difference, right, then the units on delta phi over delta t ought to come out to volts, all right? So that is what we want to show. Now the first thing to do here is to note, once again, that delta phi has units of Teslas times meters squared. Now Teslas, okay, have the units of newtons per coulomb times meter per second, right? Newtons per coulomb times meter per second. So then when I multiply my Teslas by meters squared, then I'm going to get newtons times meters squared over coulombs times meters per second. And something else I can do, since this is meters per second, but meters per second is in the denominator, I can move the s up to the numerator and get newtons times meters squared times seconds over coulombs times meters. Okay. Now, newtons times meters is joules. So if I take one of these meters and multiply it by newtons, I'm going to get joules, but I still have one of the meters left over, and I still have my seconds, and I have my coulombs and my meters. Okay. But what I can do now is cancel out the meters, and I get joules times seconds per coulomb. But joules per coulomb is volts. So Teslas times meters actually turns out to be the same thing as volts times seconds. Okay, so the units on phi, or technically the change in phi, but the change in doesn't matter, because since I'm subtracting, the units on change in phi and the units on phi have to be the same thing, right? So the units on phi, or delta phi, are volts times seconds. So when I take my delta phi, Teslas times meters squared, and divide that by seconds, that's the same thing as taking volts per second and dividing it by seconds, and volts per second, or I'm sorry, not volts per second, but volts times seconds, and divide that by seconds. Then the result is just volts, right? My result is just volts. So that is how to show that the units on the change in flux over time is in fact volts. Okay, so that is problem 23.7. 23.9, we've got an MRI technician, and he's moving his hand into a region of low magnetic field strength, or from a region of low magnetic field strength into a region of strong magnetic field strength, 2 Teslas, in an MRI scanner. And his finger, his wedding ring, is pointing in the direction of the field. So as he pushes his hand into this field, the circular part of the ring is capturing the flux head on, right? And so once again, the normal of the ring is going to be in the same direction as the field, right? So the normal is here, and the field is the stuff in blue, and they're in the same direction, so the cosine is going to be 0, all right, between the field and the normal there. So the induced EMF, all right, is going to be the change in flux over change in time, and we're given that the radius of the ring, okay, we're actually given the diameter, but we'll translate this into radius, 1.1 centimeters. The initial field is weak, right? So it has a very low magnetic field initially. So we're going to essentially call that 0, right? And then he goes to a final field strength of 2 Tesla, and that's a very strong magnetic field, right? Very strong magnetic field. And he does this, he pushes his hand into that region in about a quarter of a second, right? So the EMF is just going to be the change in flux over the change in time, And the change in flux is going to be the change in the quantity BA. Now, the definition, of course, is BA cosine theta, but again, since the angle is 0, cosine goes to 1, right? And the angle does not change between the initial and final situation. So we don't have to worry about that. So this is just the final magnetic field multiplied by the area final minus the initial magnetic field times the initial area. And it's actually the initial magnetic field being 0 that causes the initial BA to go to 0, because the A doesn't change, right? The dimensions of the ring aren't changing, just the magnetic field. So we're going to be left with B times A, where we're given the B, and then we have to calculate A, right? So remember that the area of a circle is pi r squared, right? So that's the area of a circle, is pi r squared. And so we're given the radius, and we translate that into meters, into 0.0110 meters. And here we have our pi, and here we have our squared. We divide that by our time, and we get our final voltage, potential difference, induced EMF, if you will, of 3.04 times 10 to the negative third volts. Now, this particular question also says, now discuss whether this current would significantly change the temperature of the ring, right? So as the ring gets put into the magnetic field, it has a current induced in it based on its own internal resistance and the potential, right? The induced EMF. And so the question is this going to be enough to significantly change the temperature of the ring? For reasonable estimates of the resistance, right? Maybe perhaps say 1 milliohm, okay? You can put 1 milliohm in there and you can calculate the current, and the current actually is not enough to significantly change the temperature in the ring, okay? It's just not quite enough. Now, what about the next problem, 23.19? So at what speed must a sliding rod in figure 23.11 move to produce an EMF of 1.0 volts in a 1.5 Tesla field, given that the rod's length is 30 centimeters? I'm going to leave it to you to look at the figure. Okay, but this is an example of motional EMF, okay? This is the so-called railgun problem, right? This is the so-called railgun problem. And what this says is, if I have a bar moving in a field that's also connected to conductors that have current running through them, then actually I don't have to necessarily have current running through them. I can induce the current running through them in this situation. I can do one or the other. But in any case, okay, the induced EMF is going to be given by the field strength multiplied by the length of the bar multiplied by the velocity that the bar is traveling with. And again, this is when the theta is parallel with the area, or the angle between the field and the area, the normal of the area are parallel. Okay, I have a sine theta in there if they are not. All right, but in this case, if you actually go and look at figure 23.11, then you'll see that they are indeed parallel. Okay, so in that particular case, we're given the EMF, we're given the field, and we're given the length. So at this point, it is just literally putting it into this equation and solving for the velocity. Okay, and I get 2.22 meters per second. One thing to note, right, as I said, this is the railgun problem. So the railgun problem occurs, a railgun situation occurs, I guess I should say, if you have a metal bar and it can slide along rails and you put current through those rails, then that current will produce a magnetic field inside the area, and that magnetic field, as it changes, will produce an EMF